In this video, we're going to learn how to use a compound's AXE notation in order to determine what that compound looks like in 3 dimensions. Before we do that, however, we need 2 pieces of information, starting with what the molecule looks like in 2D, in order for us to be able to identify what the compound's AXE notation is. Because if we don't know what the compound looks like in 2D, we won't be able to figure out how many bonding groups and how many lone pairs surround the central atom. Once we have these 2 pieces of information, however, we can then begin to figure out what the structure looks like in 3D. So as a review of VSEPR theory, valence shell electron pair repulsion theory, that theory simply states that since bonds and lone pairs are made of electrons, and since electrons are always going to be repelling each other, they want to simply maximize the distance away from each other so that the negative charges in the bonds are as far apart as possible. Now, if we take a look at an AX2 molecule here, for example, carbon dioxide, we know that each of the double bonds containing 4 electrons, 2 pairs of electrons, these 2 double bonds will want to be as far apart as possible, and since there are no other bonding groups or lone pairs, the biggest angle that they can make away from each other is 180, which is why in an AX2 molecule, the bond angle that we find is 180 degrees, again indicating that this is as far away that electron groups can be from each other. Every molecule is given a name that describes their geometry, where the atoms and bonds are in relation to each other. So an AX2 molecule is what we call a linear molecule, because if we align carbon and the 2 oxygens in carbon dioxide, they form a straight line. Fairly simple. So if we take a look at AX3, the same principle applies. If we consider BH3, there are only the 3 bonds, the 3 single bonds, each of which is a single bonding group that surround the central atom, which means that if we have 3 pairs of electrons that all want to maximize how far apart they are from each other, the biggest angle that each pair can make around a single central atom is 120 degrees, which is why this structure is what we call a trigonal planar structure. Planar is simply a word that means flat, and trigonal meaning that there are 3 substitutions that allow for a triangular shape to be constructed. Where everything gets complicated is where we have anything larger than AX3, which would be an AX4 molecule and up, because for the first time we see bonds, or rather we see electron attachments that are no longer planar. So in order to talk about any molecule that is bigger than AX4 in terms of the number of attachments, we need to actually look at how we represent those in 3D. And to do that, we can turn to the Java applet that I introduced in the previous video, the PhET molecule shape simulator. So if we wanted to build CH4, if we wanted to build methane, well, that's a carbon connected with 4 hydrogens connected by 4 single bonds, so 1, 2, 3, 4. Now, if we try and make the entire molecule flat, if we try imagining that this molecule is on a piece of paper and that all of these bonds are flat, that is no longer possible, because the electron pairs in each bond want to position themselves as far away from each other as possible, and now we have 3 dimensions instead of 2. So if we look at these 2 hydrogen atoms and the 2 bonds that connect them to carbon, these 2 look reasonably flat, but we can see this hydrogen atom here is positioned behind the carbon atom and the 2 flat hydrogens, while this hydrogen atom here is positioned in front of the carbon with its bond pointing forward. So this is what we mean when we talk about 3D molecular structures. So how do we represent this on a piece of paper? Well, we can see that these bonds here, what we call planar bonds, remember that the word planar is just another word that means flat. Planar bonds are drawn in exactly the same way that we draw normal 2D Lewis structures as straight lines. Now, this bond here, which kind of looks like a series of dashes, indicates that the bond points backwards, which means that this hydrogen atom and the bond that connects it to carbon are actually behind all of the atoms and bonds that are planar. Whereas this bond here, which looks like it's getting bigger as it comes towards you or towards the screen, bonds like this indicate that bonds point forward, which indicates that this hydrogen and the bond are in front of any molecule, any atom or any bond that is planar. Now, when drawing 3D Lewis structures like this, the recommendation is to keep as many of the bonds and lone pairs as planar as possible, especially when it comes to multiple bonds. And let me give you a reason why. Let's say that you wanted to draw the 3D structure of carbon dioxide. However, we wanted to show what these double bonds look like in 3D. Well, what would that look like? Well, if we go back to our molecular shape simulator, let's look at what carbon dioxide looks like if we don't want to draw it flat like this. So, as with every AX2 molecule, carbon dioxide can be visualized completely flat like this molecule here. However, if we tilt it like this, now we can see that this double bond and the oxygen connected to it are pointing forward towards the screen, and this double bond is pointed backward behind the carbon atom. Now, if we wanted to represent it in 3D, we would have to draw it something like this, which actually looks rather silly and provides a needless amount of work to show that this molecule is still linear. So again, generally it is much easier to draw as much of the molecule as flat as you possibly can without resorting to having to draw bonds and lone pairs in 3D. For the introduction part, this video will consist of only structures that have bonds as attachments rather than lone pairs, as lone pairs tend to complicate things. So if we take a look at one example that isn't something that we've constructed, let's look at PCl5, because not only does this have an expanded valence shell, but its 3D structure is quite a bit more complicated. So if we try using this as an example, we know that phosphorus starts with 5 valence electrons, chlorine starts with 7. 7 times 5 is 35 electrons, plus the 5 from phosphorus is a total of 40. So we know that phosphorus goes in the center because it has 1, 2, 3 unpaired electrons, which means that chlorine goes on the periphery because it only has 1. So we know that phosphorus is our central atom, so there is our A. And then we need to connect 5 chlorines to the central phosphorus atom. So let's go ahead and add the single bonds on 1, 2, 3, 4, 5. And if we used 5 single bonds, that means that we used 10 electrons, which means we have 30 electrons left. Now, because phosphorus has 5 bonds, we're not going to put its lone pair back. So let's put chlorine's 3 lone pairs each back on. There's 6, 12, 18, 24, 30 electrons. So, given that we had 30 electrons left, all that we do to add in the 30 electrons that we have is put all of chlorine's lone pairs on, and that brings us to 0 electrons. Now, if we want to calculate phosphorus pentachloride's AXE notation, we know that phosphorus has no lone pairs, so there is no E here. And because it has 5 single bonds, that's 5 individual bonding groups. So this would be an AX5 molecule. Next, we can go into our molecular shape simulator and find out what an AX5 molecule looks like. So let's get rid of our carbon dioxide. This is our central atom, phosphorus, and let's put 1, 2, 3, 4, 5 peripheral atoms on. So if we orient as much of this molecule as possible to be planar, we see that the top and bottom chlorines are flat, with this one going off to the left, as being flat, we see that this chlorine atom here, let's straighten this molecule out. This chlorine atom here is pointing behind the central atom, and this chlorine atom here is pointing in front or forward from the central atom like this. In our introduction to this molecule shape simulator, I referred to these two atoms here as being axial because you can rotate these three around it like an axis, and these three as being equatorial because a circle that goes around an axis in the middle is what we call an equator. So if we look at the bond angles that we see, this angle between the axial chlorine up top and the equatorial one that is planar looks like it's 90, and the angle between the two axial chlorine atoms looks like 180, while if we turn the molecule like this, it looks like these three form three 120-degree angles around the equator of this molecule, and if we put the bond angles in, that's exactly what we see. 180 between the two axial and 120 degrees between each of the equatorial chlorines. So let's go about trying to represent this in our new form of Vesper-based Lewis structure. So if we draw our phosphorus, we know that the two axial chlorines are 180 degrees apart, and we can put their lone pairs back on here. Then we can put this third chlorine here such that we can see a 90-degree angle between each of these chlorines, between this equatorial one and the two axial chlorines. We remember that one of our chlorines was positioned behind the central atom, behind the phosphorus, like this, and the last chlorine was the last equatorial chlorine was positioned forward from the central atom in front of it like this. And that's how we use 3D Lewis structures in order to represent the geometry. If you want this to be complete, we can label the bond angles as well. So the bond angle between these two chlorines would be 90 degrees, and the bond angles between each of the equatorial chlorines would be 120. Finally, you can also use the molecular shape simulator in order to find out what the shape name is. If you click on molecule geometry, you can find the name of this shape as what we call trigonal bipyramidal or trigonal bipyramidal. That means that basically you can draw two pyramids, one up top with a triangular base and one on the bottom with a triangular base like this. So all of these shape names, so this one, trigonal bipyramidal, is simply pyramidal is simply a way to remember what the geometry of the shape is, because it will usually be a descriptor of the type of shapes that you can visualize given the molecular geometry. Before the next video, what you can do is practice number one, making sure that you can draw the 2D representations of all of the different molecules listed as practice problems, figure out what the AXE notation was, and use the molecular shapes simulator here in order to construct the geometry, and then use the geometry here that you can see in order to accurately draw what the 3D representation of that molecule is, as well as start learning the shape names for the molecular geometries. And in the next video, we will look at representing molecules in 3D that have more than just bonding groups in terms of the attachments.